So hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Nigel David HIGSON. I see that you have a middle name as well, to our North Atlantic Non-Commutative Geometry seminar. So Nigel, it's not your first time that you act as a terminator. You are the last speaker of a semester. And if you remember some years ago, there was a big poster in Warsaw with your face and some thoughts in your mind. Non-commutative geometry thoughts, yes. Because then you ended our 4-year program in transfer of knowledge, and today you just ended the semester. But anyway, yeah, perfect for the job, and we are very happy to have you here. So it's the OCA principle and the K-Theoretic perspective on the Langlands classification. Nigel, it's our pleasure. The Zoom is yours. Take it away.
Excellent. Thank you very much. Let me add one apology to Piotr's apology, which is that in my house, workers are replacing the roof as we speak. And so there may be some environmental noise. I was driven to the basement. I'm as far away from the roof as I can possibly get inside my house, but still there may be some banging and so on. So my apologies for that. I shall talk, as you see, about the OCA principle and the Langlands classification, and a lot of what I'll be doing in the talk is explaining what these words mean and eventually what they have to do with K-theory and sister algebras of reductive groups. That's the direction in which I'm heading. This is joint work with Jacob Brad, who's a student of mine here at Penn State. Actually, he got on the last plane to Australia back in March of 2020. And he is sitting out the pandemic in Australia, which is the place to be. So, you know, this is a clever guy. And I'm very happy to have him as my student and working on this project. And this is a little cartoon of what I hope to achieve in this lecture. I should say that this is very much a work in progress, and you'll see that as time goes on. There are many theorems with quotation marks around them, which are not exactly theorems yet. The state of play is we understand everything, thanks to Jacob's efforts for SL2R. And for the most part, that's likely to be a reasonable indication of what's going on. And we understand many things for groups other than SL2R, but we certainly don't understand everything. So these dots will represent eventually K-theory groups, and the various arrows between them will be homomorphisms of K-theory groups. And they're all supposed to be isomorphisms. And so it's supposed to be the case that the famous Kasparov isomorphism for K-theory of sister algebras of reductive groups breaks up into a number of parts. This Paley-Wiener part on the top is no big deal. It's almost an equality, but then the other two parts are very interesting. This OCA map, which I'll describe, and then this Langlands map, which I'll describe. Of course, neither OCA nor Langlands ever had anything to do with K-theory that I'm aware of, so I'm just borrowing their names. Hope they don't mind. All right, let me start with some interesting ancient history in K-theory. This is from 1967, which is kind of amazing if you think about what K-theory for Banach algebras was in 1960. And it didn't really exist. And yet, nevertheless, Mark Nowonosky proved this amazing theorem. He was a brilliant fellow, but he proved this theorem and then he decided to become a lawyer. So go figure. But before he left to be a lawyer, I think he fled the Soviet Union and became a lawyer somewhere more profitable. Before he left, here's the theorem he proved. If you have a commutative Banach algebra, then the Gelfand transform, which we all know maps is a homomorphism from the algebra A to the functions on the spectrum of A, the maximal ideal space of A. Of course, it's nowhere near an isomorphism in general. It is for C-star algebras, but otherwise it's not. Nevertheless, it always induces an isomorphism in K-theory of Banach algebras. And I learned this theorem, the statement of this theorem, when I was learning about K-theory from Joe Taylor's notes all the way back in the dark ages. And so I've always known about this and been fascinated by it. It's just the most beautiful and simple and appealing statement. And this is related to the Oka principle, which I mentioned in the title, let me try and explain what's going on there. Suppose you have a compact subset of Cn, then that compact subset has a sort of convex hull, a polynomially convex hull that you can define, and it's the thing in brackets here, in these brackets here. I forgot to highlight this in some nice way. It's just a set of all points at which polynomial functions are dominated by the values of the same polynomial functions on K. In the case of the complex plane, if you're in C1, what this polynomial convex hull condition has to do is that it fills in the holes inside of K. So a polynomially convex subset of the plane is just a set whose complement is connected by Runge's theorem. But in higher dimensions, that's not the case. And of course, a compact set will be called polynomially convex if it's equal to its own polynomially convex hull. And any compact set, as long as you can fit it inside of Rn, can be realized as a polynomially convex set. So there are lots of examples of these. And here's one formulation of the Oka principle, I guess a mildly special case of the Oka principle, proved by Grout in the, I guess in the 50s. Suppose you have an open set instead of a closed set, compact set, and suppose it's polynomially convex. I mean that all of the compact subsets have their convex closures, polynomially convex closures inside of U. In that case, each time you have a topological vector bundle on U, you can equip it with a unique up to isomorphism holomorphic structure. So there's no difference between holomorphic vector bundles up to isomorphism and topological vector bundles up to isomorphism. That idea that holomorphic equals topological is what the Oka principle is generally about. And this is maybe the most famous instance of that, as I say, due to Grout. And here's what this has to do with Banach algebras. If you happen to have a compact and polynomially convex subset of Cn, and if you build a Banach algebra just by taking the uniform closure of the polynomial functions on K, I mean, of course, complex polynomial functions, polynomials in Z, not in X and Y separately. If you take the uniform closure, then it's easy to see that the Gelfand spectrum of B of K is just K. Evaluation at the points of K gives you the spectrum. And so the Gelfand transform is something very simple. It's just the inclusion of this subalgebra of C of K into C of K. And so according to Oka, this is an isomorphism in K theory. This is not a simple result. The image of B of K inside of C of K, well, it's a closed subalgebra, and it's certainly not dense by any means. It's not all of C of K. So none of the standard techniques apply to indicate that this map is an isomorphism in K theory, and yet it is. And I'll say a little bit about why that is a little later in the talk, if all goes according to plan and we stay on time. I stay on time. And the two previous slides are obviously related to one another. In the particular case where the Banach algebra is B of K, there's not much difference between Novodvorski's theorem and Grout's Oka principle. There's a small difference because of open sets versus compact sets. And so there are some minor technical dances that need to be done to go from one to the other. Nothing too stressful. And in fact, you could say that these two theorems are basically the same. The theorem of Novodvorsky as it applies to B of K, and the theorem of Grout as it applies to an open Stein domain or a polynomially convex set, like I said it on the previous slide. And so these are basically one and the same thing. And not only that, but the B of K case of Novodvorski's theorem is really the fundamental case, the case to which all others can be reduced. If you understand that Novodvorski's theorem is true for B of K, then you can just put the rest of the argument on a postcard. There's just a few little bits of extra things you have to do to generalize from this particular Banach algebra A equals B of K to a general Banach algebra. So this is what it's all about. And the conclusion is that Novodvorski's theorem is all about complex analysis, complex variables. It's not about Banach algebras or K theory, it's about complex variables. There's something very interesting there. So that's just a little review of ancient history. Finally, a few years ago, I decided I got to get to know this theorem and understand it properly. And so I more or less did. And then with Jacob, we actually did. We studied it down to the last detail because we became interested in generalizations that I'll talk about today. And we actually have a paper on the archive if you're interested in all of the gory details of how this is proved. Well, it's a non-commutative geometry seminar, so we can't be content to stick with commutative Banach algebras. And let's just contemplate for a moment what might happen if you go beyond commutative Banach algebras. I shouldn't say for a moment, that's what the whole talk is about. We're not the first people to have thought about this. This has been around forever and ever and ever. I think Alain may have been the first person to really raise the possibility of using Ocker principles to study much more interesting, from our point of view, algebras, for example, group algebras, convolution algebras, this famous Baum-Kohn isomorphism. This turns out to be an extremely difficult project, and despite the fact that we've understood that this was a possibility for something like 30 or 40 years, very little progress has been made. And so what I'm going to try and do is explain a possible route to bring complex variables, several complex variables, the Ocker principle, into the world of K-theory of group C-star algebras. That's the good news. The bad news is that this is very much an enterprise which involves a good deal of representation theory. And at the moment, it means that we need to be in the context of Lie groups, reductive Lie groups, not in the context of discrete subgroups, which is the holy grail in Baum-Kohn land to prove Baum-Kohn for discrete subgroups of Lie groups. That's where we are right now and where we've been. Also, for the last, I don't know how many years, certainly in the last 20 years, we really didn't do anything in Baum-Kohn. We're stuck. And so it may or may not be the case that we'll get unstuck using the Ocker principle, but the work I'm going to show you today doesn't really give much of an indication that could be so. So you should think of this as more just an investigation of how representation theory, and in particular the Langlands classification, is related via the Ocker principle to K-theory of group C-star algebras, reduced group C-star algebras. And so I need to tell you a little bit about representation theory. And it was quite easy to introduce the Ocker principle to you. It's a little more involved to tell you about representation theory, but nevertheless, I'll get to work on that. So we're dealing with real reductive groups. It means they're all matrix groups, closed subgroups of matrices. And the key idea is that these groups should be closed under the transpose operation. They're subgroups of GLNR, and they should be closed under the transpose operation. And to avoid terrible counterexamples and so on, they should be connected or very nearly connected. And for this talk, I'm going to assume that G is either SLNR or SLNC. Mostly, there'll be one or two just throwaway comments about other groups as we go along. There's a lexicon which goes along with real reductive groups. Every letter of the alphabet is attached to some different type of subgroup of a real reductive group. And we'll need some of that. And rather than tell you what it all means in general, I'll just focus on this particular case of these particular matrix groups, the special linear groups, so as not to overwhelm you. And this talk is about two classes of representations, irreducible representations of such a group. And one is something that we're all kind of familiar with, and these are the tempered representations, irreducible tempered representations that were studied by Harish-Chandra and which form the subject matter of the Plancherel formula. We're all familiar with them to a certain extent because they're exactly the points in the spectrum of the reduced C-star algebra of G. So when we're talking about the reduced C-star algebra of G, it's the C-star algebra whose representations are the tempered representations of G, whose irreducible representations are the tempered irreducible representations that you see in Harish-Chandra's Plancherel formula, like the discrete series and the principal series and so on. That's one class of representations, and it's to a certain extent at another extreme are the so-called admissible representations. These are representations which are no longer even necessarily Hilbert space representations, certainly not unitary representations. This talk is not about unitary representations whatsoever, except to the extent that it's about tempered representations. So admissible is a technical condition And it means that if you restrict from G to its maximal compact subgroup, and you decompose a restricted representation into its isotypical parts, each isotypical part occurs only finitely many times. So Harish-Chandra discovered that irreducible unitary representations automatically have this property, and then others, I guess definitively Sergel, discovered that if you don't put in this condition, terrible things can happen. You can build irreducible representations, for example, infinite dimensional irreducible representations of abelian groups. You don't really want that, do you? So the admissibility condition allows you to apply the conventional tools of representation theory, like Schur's lemma, without running into functional analytic difficulty. So that we're always going to be stipulating that all representations are admissible. When you do that, you're not quite done with stipulations. When you classify these things, you want to classify them up to something weaker than standard equivalence. It's called infinitesimal equivalence. And it has to do with the fact that essentially the same representation can be realized in for example, a Sobolev space or an L2 space or a Banach space with a supremum norm or this and that. You don't want to think of those different functional analytic Banach space realizations of the same irreducible representation to essentially the same irreducible representation to be actually different. And so you invent a notion of infinitesimal equivalence, and then it turns out there's a wonderful theory that emerges. This is what Langlands and others, mostly Langlands, discovered. So every reductive group has a tempered dual, which is almost, well, it's a locally compact and almost Hausdorff topological space. It tends to look like a smooth manifold. It's a manifold with just a few singularities and a few double points and double lines and so on. It basically looks like a union of real vector spaces up to some minor discrepancies. As for the admissible dual, it basically looks like a union of complex vector spaces up to a variety of discrepancies. So these duals turn out to be reasonable objects. One of them belongs to the real world, the tempered dual, and the other, the admissible dual, belongs to the complex world, the world of complex spaces. Okay. And what Langlands did back in the, I guess, early 70s, I forgot to remind myself of the date, was he reconciled these two spaces in a beautiful and simple and totally decisive way. It's really incredible that you could do this, especially in the light of the fact that when you start to nail down what actually is the tempered dual, which even Harish-Chandra didn't do. It took subsequent efforts to work out all of the final details. It's a big mess, and yet what Langlands did was he wrote down in a simple way, so simple that I'm able to tell it to you right now, what the irreducible admissible representations are if you take for granted the structure of this space of irreducible tempered representations. And I'm not going to say too much about the actual method. I'm just going to tell you the result. There is one slide with a couple of formulas way at the end. Maybe we'll get to that. Here's how it looks in an easy case. Suppose the group is the non-zero complex numbers under multiplication. What Langlands does to describe the dual, the admissible dual, the set of irreducible, one-dimensional, not necessarily unitary representations of this topological group, what he does is he breaks G up into a sort of polar decomposition, I guess exactly the polar decomposition of the circle group times the radial direction. And then what Langlands does is he attaches to each irreducible representation a parameter, which is a pair of objects. And the first object is an irreducible tempered representation of the circle group, in other words, just an integer. And the second one is a complex number. And that's what Langlands does. And I won't take more than a moment to see how the Langlands classification works in this case. But it's worth keeping in mind this extremely simple example as we go on to something a little bit more complicated. The basic idea is that a collection of parameters will be identified, and there'll be one irreducible representation for each parameter. Not quite as simple as this, but remarkably simple nonetheless. And the key notion behind the Langlands classification, behind many things in representation theory, is the notion of a parabolic subgroup. I'll speak here of standard parabolic subgroups. That just means you fixed a certain, I don't know, orientation, if you like, For us, because we're only dealing with SLNR or SLNC, the standard parabolic subgroups are just the block upper triangular subgroups. So I showed you, for example, at the top of the screen, a certain standard parabolic subgroup of SL3R or SL3C. And there obviously are many of these. There's all of the triangular matrices, all of the upper triangular matrices. There is this particular block upper triangular matrix group. There's another, so to speak, 1-2 block upper triangular matrix group as well. And actually the 3x3 block upper triangular matrix group is allowed as well. P equals G is a legitimate standard parabolic subgroup. And each time you have one of these, it has its own sort of polar decomposition, just like we were talking about before. And here's how it works. The first, it has 3 parts, not 2 parts. P equals MAN. And the first 2 parts are analogous to what we saw in the previous slide, the usual polar decomposition. And the last part is just N, the nilpotent radical. So you have to have that here. Anyway, the M part, the phase, the angular part of the polar decomposition is just the subgroup of P, which is generated by all of the compact subgroups of P. That's one way of saying it. And in this particular case, it's just the block diagonal matrices where the determinant is plus or minus 1 on the blocks. Maybe I should have said the absolute value of the determinant in the case of SLNC. And the A group is just the radial elements. It's just in each block a scalar multiple, a positive scalar multiple of the identity. So e to the SI, e to the t times the identity, if you like, in this particular example. And then, as I said, N is just the unipotent radical. So P equals MAN, that's the Langlands decomposition, sort of slightly upmarket version of the polar decomposition that we're all familiar with. And here's what a Langlands parameter is. I can tell you almost everything, except I'll lazily not nail down one final detail. It wouldn't be that hard to do it. It's a triple. So there's going to be one such Langlands parameter for each irreducible admissible representations. This will be the space of irreducible admissible representations, which I'm describing. And so the first thing is a standard parabolic subgroup. There's just one of a finite number of possibilities there, like I was telling you. And the second thing, and this is where knowing the tempered dual beforehand is assumed by Langlands, the second thing is an irreducible tempered representation of this angular part M in the polar decomposition, in the Langlands decomposition. So it's one of the representations for the group M that Harishchandra studied. And this you should take up to equivalence, of course. And the third thing is just a character of the A group, and I've taken its logarithm here, which is conventional. So instead of talking about a character of the A group, I'm talking about a linear functional on its Lie algebra. It's just a real linear functional with values in the complex numbers. Maybe I should just say a real linear transformation. And there's just one condition called a dominance condition. And what this does is that there's an insistence that mu should be somehow positively oriented with respect to the subgroup N. I'm not going to say more except to indicate that in the example that we were looking at just a moment ago, 3x3 matrices, what mu does to a diagonal matrix, an SST matrix, is, well, it has to send such a matrix to AS plus BT. Those are the only linear functionals. And the condition of dominance is just that the real part of A is bigger than the real part of B. It always looks like this. These are just strict linear inequalities which determine what dominance is. So it's easy to calculate in any given case. And that's it. Once you have all the P's and the sigmas and the mu's, you have the admissible dual. And of course, the fly in the ointment is that you don't know what the sigmas are in general until you do an immense amount of work. But if you discount the possibility, this problem, save it to later, of classifying the tempered dual, then everything is really, really simple. What Langlands did was point out some really simple and beautiful way of understanding all representations, just in terms of tempered representations. And let me tell you how Langlands builds the corresponding representation. You take the standard parabolic subgroup, MAN, it's actually a semi-direct product group because the block diagonal part, which is MA, normalizes the unipotent part, which is N. And that means you can think of MA, the block diagonal part, as a quotient of P, not just as a subgroup of P. It's actually really a quotient of P. So each time you have a representation of MA, you can think of it as a representation of P. And you get a representation of MA just by tensoring the representation sigma of M, which you are given in the Langlands parameter, with the exponential of mu to make it into a group representation rather than a Lie algebra representation. You take this tensor product of representations, of course, the exponential is just a one-dimensional representation. And then you do induction in the sense of Mackey, for example, from P to G. And that gives a representation of G, an admissible always representation of G. Strictly speaking, you want to stick in a small normalizing factor or a row, half sum of the positive roots, in order to ensure that the induced representation of the contragradient is the contragradient of the induced representation. There's a preferred normalization so that induction commutes with taking contragradients, and I didn't do it here because I was too lazy, but it should be there. So now you obtain a representation. Of course, you can do this whatever mu is. You don't need the dominance condition to build this representation, and we'll use that observation later. But if the representation, if mu, the character mu, is dominant, then what Langlands showed is that this representation, which I built, usually this thing is an irreducible representation with probability 1. It actually is irreducible. But whether or not it actually is irreducible, it always has a unique irreducible quotient. Unique irreducible quotient is kind of a remarkable thing. And so you get an irreducible representation out of P and sigma and mu all put together. And then the other thing that Langlands proved, the rest of the classification, is that every irreducible representation is obtained according to this prescription exactly once. There's some preferred P that you have to start with if you're given the irreducible admissible representation, and then a preferred sigma and preferred mu, and Langlands explains how you get all of these pieces. It's a remarkable theorem. It looks like a hopeless problem to classify these representations. It looks hopelessly worse than understanding temporal representations, which is already bad. But in fact, it has this remarkable resolution. And this is ground zero in representation theory. If you want to understand, for example, which are the unitary representations, first of all, you have to give each unitary representation a name so you can talk about it. And that's done using the Langlands classification. This is wonderful computer program, Atlas. And there's a command in Atlas called isUnitary, ? And so you can ask it, is this representation unitary? And you tell it in the Langlands classification which representation you're talking about. And it says, well, I don't know. I'll have to think about that. And then it does its thinking, and then it gives you the answer. It used to be the case that the trivial representation was the hardest representation for it to answer, but they fixed that, and now it automatically tells you the trivial representation is unitary. Anyway, let's see how this all works out in an easy case. In some ways, SL2R is a really good illustration. In some other ways, it's not. It's a little too simple and therefore misleading. Nevertheless, it's something that we can easily wade through very easily. First of all, there are only two standard parabolic subgroups. There's all of G, which is allowed, like I said. And what are the Langlands parameters for all of G when the parabolic is all of G? Well, this polar decomposition is very simple in that case. The MAN decomposition of all of G is that M is all of G, and there's no A and there's no N. And so G equals M, and the tempered representation part of a Langlands parameter, of course, just gives you a tempered representation of G, tempered irreducible representation of G. So what you see in the Langlands classification is that G itself, thought of as a standard parabolic subgroup, accounts for the tempered dual of G. And that's it. From now on, the rest of the discussion is about the strictly non-tempered representations. And they all have to be attached to the only other parabolic subgroup out there, which is the minimal standard parabolic subgroup out there, which is the minimal parabolic, which is the group of all upper triangular matrices. And I've shown you its polar decomposition, its Langlands decomposition. The M group in this case is just a two-element group, plus or minus the identity. And the A group is one-dimensional, and the N is, well, what it is. I'll be talking about the minimal parabolic subgroup more in just a moment, and maybe I should just emphasize here while we're staring at this example that for the minimal parabolic subgroup, the M group is always compact. So in theory, we ought to know everything about it. And of course, the A group is always abelian. So in theory, we ought to know everything about it too. So this is the one and only other parabolic subgroup we have to understand. We have to study all of the Langlands parameters for this. Well, that's easy. It's just an element of the dual of Z mod 2. There are just two such elements in the dual of Z mod 2. It's just a character on the group R with a dominance condition, and that's it. So what is the dominance condition? Did I write it down? Yeah, I did here in green. The dominance condition is easy to understand. If you identify the complex dual of R, the group of all homomorphisms from the group R to the complex non-zero complex numbers, if you identify that using the logarithm with the complex numbers, then dominant just means positive real part. And sigma, as I said, in a Langlands parameter in this case, is just one of two things, either the trivial representation of Z mod 2 or the other representation of Z mod 2. And so what the admissible dual looks like after you subtract out the tempered dual. We're not talking about the tempered dual here, that was in the other part of the Langlands classification. After you subtract out the tempered dual, it's exactly what you see in green here. It's just two open half planes. That's it. And I colored some points in these open half planes with dots in a slightly darker green. Those are the only points where the induced representation, which Langlands uses in his classification scheme, those are the only places where that induced representation is is reducible, not irreducible. So the Langlands quotient is non-trivial for this very small discrete selection of points, and everywhere else, it's already an irreducible representation that you get by parabolic induction. And what are those Langlands quotients, by the way? Well, SL2R has lots of finite dimensional representations. There's one finite dimensional representation for each, well, for example, in each dimension. And you see here, there's one green dot in each dimension. The first dot here is at the point n equals 1. The next one here is 3, and here's 5. What about 2? Well, it's here and here. Okay, 1, 2, 3, 4, 5. So the first 5 irreducible finite dimensional representations correspond to these green dots. You might ask yourself, what about the rest of these parabolically induced representations which are not irreducible and which have these finite dimensional Langlands quotients? Aren't those other representations of G, how do they fit into the Langlands classification? They must correspond to something else, according to Langlands, because he's supposed to have classified every single representation. Well, they do. It turns out all of those other representations are tempered. Each of those other representations appearing in the kernel is, well, a direct sum of two of the famous discrete series representations for SL2. And so we're not talking about them in this picture, which is all about the explicitly non-tempered representations. So it's all very beautiful how it works out. And if you move the tempered representations out of the picture, it's even more beautiful still. What you see for the admissible dual minus the tempered dual is just two half planes. That's going to be important for what follows. All right, and so I want to connect that type of picture that I was just showing you with convolution algebras. And what I'm going to do is build various algebras of matrix valued functions, operator valued functions on the spaces that I just showed you. And in doing so, I'm going to focus entirely on the minimal parabolic subgroup, of course, for SL2. That's what we were talking about, because that was the only non-trivial parabolic subgroup. But whether or not there are other parabolic subgroups, as for example, there are when it's SL3, not SL2, whether or not they are, I'm not going to pay any attention to them right now. We're just going to be discussing the minimal parabolic subgroup. So for example, for SL3, it's all upper triangular matrices. And now I'm going to also look at the space of all possible parameters that you get by looking at sigmas and mu's like in Langlands, except that I'm going to drop this for now, this dominance condition. I'm just going to look at all conceivable mu's. They form a complex vector space, not a chamber in a complex vector space, but just a complex vector space. And I'm going to look at all conceivable sigmas. Well, M is always a compact group I mean, in the examples that we were looking at, it's always a compact abelian group, but in general, it's always a compact group. And so the set of all possible sigmas up to isomorphism is always a discrete space. So I'm studying a slight variation on what Langlands would do, and I'm studying a parameter space, which is just a discrete space times a complex vector space, or if you like, it's just a discrete union of complex vector spaces. That's a certain topological space. Well, actually, it'll be important that that's a certain complex manifold, and that's what I want to be playing around with. Okay, no dominance in the discussion right now. Just we have a certain space in mind, a geometric space in mind, and it's just a union of complex vector spaces. Like you see in this picture down here, this is the picture for SL2. Now it's two whole complex one-dimensional vector spaces. And I want to think of this as a base space for a certain vector bundle. And the vector bundle is extremely easy. Given a point in one of in this space, in one of these green planes, for example, that I've drawn for SL2, given a point, it's exactly the data you need to form by parabolic induction a representation of G. Namely, you induce from the minimal parabolic to G, sigma tends to the exponential of mu.
So
and you get a certain...
You don't take the irreducible quotients then?
No, I'm not taking irreducible quotients.
Okay, thank you.
Yeah, nothing at all. So this is an extremely boring vector bundle. It's even more boring than I've told you so far, because these fibers, which are the induced representation spaces, they don't actually depend on the continuous parameter. So in each component, I'm looking at the constant vector bundle whose fiber is whatever it is, this induced representation space. So there's not much going on with this vector bundle. Nevertheless, I want to play with it for a little bit. What makes it interesting is that each fiber of the vector bundle is a different representation of the group G, and you'll see that playing a role in just a moment. And so I want to play with this a bit, and I want to build in particular various algebras of endomorphisms of this vector bundle. I'll build an algebraic version first, and then I'll build a continuous version, and then I'll build a holomorphic version. And you can see where this is going. There should be some relation between the continuous and the holomorphic version using Occam's principle, and so on and so forth. And to keep matters a little bit under control, actually, it's a little more than keeping matters under control. It's kind of essential to the whole enterprise, but I won't go into that in too much detail. I want to chop down this vector bundle. It's an enormous infinite dimensional vector bundle. Each of these induced representations, I guess I didn't say it, but they're all infinite dimensional representations of G. But if you restrict them from G to the maximal compact subgroup of G, for example, SO2 in the case of SL2R, they break up into isotypical parts. And I just want to look at a finite direct sum of isotypical parts. I'll choose a collection S of irreducible representations of K, and the corresponding finite isotypical part of all of these induced representations. I'll get myself now a boring, trivial, locally trivial, I mean, component-wise trivial, finite dimensional vector bundle on this parameter space. I'll show you some examples in a moment. And now I want to build an algebraical algebra. Here's what I'm going to do. In each fiber of this vector bundle, I have a representation of G. Actually, I have a finite dimensional subspace now of a representation of G. And on that representation, the Lie algebra of Gx. And so I just want to look at all operators that I get on the finite dimensional part of the infinite dimensional representation by compressing the action of G. And that produces, for each time I have an element of the Lie algebra of G, that produces an endomorphism in each fiber of this bundle, and therefore an endomorphism of the bundle. And I get in this way a certain algebra of endomorphisms of a finite dimensional vector bundle over kind of a boring base space. And this has a name in representation theory. It's called the Hecke algebra. It's actually a rather interesting algebra to think about. And what it always looks like is just an algebra of matrix-valued polynomial functions on a space, which is just a disjoint union of finite now disjoint union of vector spaces, complex vector spaces. Here's what it looks like in the easiest possible case. There's a fascinating series of papers by Bernstein, Gelfand, and Gelfand from the 1970s where they took it upon themselves to calculate these things in a few examples. And what you rapidly find is that the calculations become incredibly and unmanageably difficult. But for SL2, you can actually do it. So here's what it looks like. Let's take the set of irreducible representations, this finite set of irreducible representations of SO2 for the sake of this example, to be all of the weights between -2 and 2. That just makes it a little bit interesting. Not too big that we can't understand it, and not too small that we don't see all of the phenomena. Okay, and now you can say exactly what this first of all, what the vector bundle is after you compress to these isotypical parts, and then exactly what the Hecke algebra is. It's a direct sum of two parts because there were two components to the base space of this bundle. It's a direct sum of two parts. So in one part, the Hecke algebra consists of 2x2 matrix valued functions, and in the other part, it consists of 3x3 matrix valued functions. And you can calculate what's going on, and here's what's going on in this particular case. And it's kind of interesting what you get, as you can see from the formulas here. If you take z equal to 1 in the second component, what you'll see is that in the second row, the first and the third entries have to be 0 because of the z-1 factor. And what that means is that the 2 term is sort of a subquotient of, a quotient, not a subquotient, but a quotient of the entire three-dimensional representation. That is the Langlands quotient at z equals 1. That's actually the trivial representation of SL2, or it corresponds to the trivial representation of SL2. So you can do a little bit of thinking about what's going on here, and you can see the Langlands classification actually staring at you, or not staring at you, waving at you from these matrix formulas. Anyway, I just wanted to give you a sense of what these guys look like. It's very interesting to try and understand what these look like in general, but it's also fantastically difficult because as soon as you know what these algebras are, if you could know what these algebras are up to isomorphism or up to Morita equivalence, then you would know what is the full category of admissible representations. I mean, not just the irreducible elements of this category, the irreducible objects, you'd know the whole category. So these algebras are incredibly rich, and they stand for, or they represent the entire category in algebra form. That's both interesting and daunting. It means that you don't have much of a hope to understand these algebras except in a few simple cases, because they include too much information. And we're going to try to remedy that problem of these algebras being overburdened with information by building different algebras. Well, the different algebras will be equally overburdened with information, but we're going to take their K-theory, and that'll wash us down to something which is a little more easy to understand. So the strategy is to replace the A algebra, which belongs to the world of algebra, polynomial algebra, with an algebra I'll call curly C. Curly C will be, well, not quite a Banach algebra, but a Fréchet algebra, an inverse limit of Banach algebras. Curly C will be just as complicated as curly A, but now you can take the K-theory of curly C because it's a Fréchet algebra, which is not something you can do with curly A, at least in a way which resonates with everything that we know in this seminar about K-theory. Anyway, what is it? Now you've probably read way ahead of me. Curly C of G is just the algebra, instead of polynomial matrix valued functions, it's continuous matrix valued functions. But point-wise, they should look exactly the same as the elements of A of GS. So whenever, for example, a particular matrix element entry of all of the elements in A of GS, whenever that element is 0 for all possible elements in A of GS, like you saw in the previous example at z equals 1, well, it has to be 0 in C of GS as well. And if there are identities between what happens, for example, at z equals 1 and z equals -1, well, those identities have to be replicated inside of C of GS as well. Okay. And a very nice way of expressing this is what I've written here, which is not due to me, that on finite subsets of the base space, all of these continuous functions should agree with the restrictions of the continuous functions you get just from the polynomial functions. And finally, in order to get some reasonable Frechet algebra, now we're going to insist that all of these functions converge to 0, not uniformly across the entire complex vector space, but if you constrain the complex vector spaces in the real parts to lie in compact sets, if the real parts are constrained, then in the imaginary direction, you should have rapid convergence to 0. So in the pictures that I was drawing on vertical strips, in the case of SL2, one should have rapid convergence to 0 as you travel up and down the vertical strip. But there's
Nigel, just a qualitative question.
Yes.
So I mean, so what you are saying is that on finite sets, the situation is the same, but somehow what you want is to have a control of the behavior at infinity.
Yeah.
Yeah. So is there a way to define a topology by which, I mean, they are related, these two algebras, in some more precise manner? Or?
Yeah, it's an extremely interesting question. Of course, you can get elements of this algebra sort of systematically by taking polynomial functions and then just multiplying them by complex Gaussians, something like that.
Yeah, sure, yes.
I do not know of a way of linking together this Frechet algebra, curly C, and the algebraical algebra, curly A, in a more, I don't know, substantial way than that. Mm-hmm. It's one of the problems of C-star algebras or Frechet algebras like this one here.
Sure, of course, yes.
That then, they're far from Noetherian. It's much preferable in many contexts to work with curly A and not curly C. It's a much better algebra.
Sure.
And it would be lovely to have some intermediate algebra, curly A, curly C.
You mean it is the usual
AC
story in quantum field theory where you pass from unbounded operators to the C-star algebra.
Yeah. Here it's, I mean, well, let me continue. Here you'll see why it may not be obvious at this point why you should make your life difficult by dealing with continuous functions when this perfectly good algebra curly A existed. But I hope it'll become clearer as we go along. As I say, at the very least, you can take the K-theory of curly C. Certainly, we know that off the bat.
Sorry, may I have a question?
Yeah, please.
So this rapid decay means something like for a Schwarz function, or?
Yep, exactly. It should decay to 0 in the imaginary direction of these complex vector spaces faster than any polynomial goes to infinity.
Okay, thank you.
Okay. All right, so here's something a little more friendly, maybe to this seminar, which is the reduced C-star algebra of G, like, for example, the reduced C-star algebra of SL2. I'm going to give the C-star algebra of G the same treatment that I gave these Heck algebras that I was discussing before. Namely, I'll compress them to various isotypical K-isotypical parts of L2 of G. So C-star reduced of G is acting by, say, left translation on L2 of G. Therefore, K is also acting by left translation. And I mean, I want to compress to the SK left translational isotypical part of L2 of G. Okay, I don't want the translation action of K to commute with the translation action of G by using the right translation. That would be a bad idea. So this thing is a subalgebra of C-star reduced of G, and you get C-star reduced of G back by taking the direct limit as the finite set S gets bigger and bigger and bigger. So this is just a small corner of C-star reduced G, and it's convenient, and maybe even a little more than convenient, to work with these corners.
Okay. Sorry, may I interrupt once more?
By all means.
So compression, you mean the restriction and then applying the projection, yes, from left?
That's correct. Yep.
Okay.
Yep. Okay, if you think of an element in the C-star algebra as some sort of giant matrix acting on L2 of G, if you choose an orthonormal basis inside of L2 of G, then what I'm talking about is just chopping out a certain corner of that matrix.
Okay, thank you.
And now there's an interesting relation between the curly algebra that I built and the reduced C-star algebra. Now this is a reason for not dealing with polynomial functions and dealing with functions which can converge rapidly to 0. In fact, I put in rapid convergence to 0 precisely to make this a true theorem. The little quotation marks in green, as I'll explain on the next slide, mean that we didn't prove this 100% yet in every case. So strictly speaking, I shouldn't call it a theorem, but I have serene confidence in this theorem. I have another theorem later on with triple quotation marks. I'm not so confident about that, but this one, I'm just attempting to be honest here and saying that not every T has been crossed or I dotted. Anyway, there's a canonical homomorphism of algebras, Frachet algebras, from curly C of G of S, this matrix function object that we've been discussing, to the reduced C-star algebra of G. And here's how you characterize it, not so much how you define it maybe, but here's how you characterize it. If you have a tempered irreducible representation of the group G, in fact, it's known, thanks to a theorem of Harris-Chandler, that that tempered irreducible representation of G will occur as a subquotient of one of these parabolically induced representations from the minimal parabolic that I've been talking about. So this tempered irreducible representation of G, in other words, this representation of C star of G, it will occur as a subquotient in one of the fibers of this infinite vector bundle, infinite rank vector bundle that I've been talking about. Now, because of the conditions on the algebra curly C, if I take a function in curly C and I just evaluate it on that single irreducible representation, of course, on that single induced representation, I'll get an endomorphism of that induced representation. But the conditions imply that that endomorphism will pass to the subquotient representation. And so it'll give me an endomorphism of the subquotient representation, this hypothetical tempered representation. So now I have two endomorphisms of the same tempered irreducible representation, and the condition which characterizes alpha is that those should be the same. And when I say the same, I'm invoking Schur's lemma here to identify the two spaces up to a essentially canonical isomorphism. So the word the same, or in this case, agree, that I used on the last line, actually means something. So that describes what the homomorphism does. And now you can prove, at least up to green quotation marks, that there is such a homomorphism. And it's basically surjective. It's basically surjective. It's not exactly surjective because I put this rapid decay condition on the curly C side, whereas on the C star side, it's more like a C0 condition. And they're not exactly the same. On the other hand, you need to put in the rapid decay to be assured that this homomorphism exists. However, this map is close enough to being surjective that it induces an isomorphism from the quotient by its kernel to the C star algebra of G at the level of K-theory. This is now holomorphic closure. This is not a difficult result. This follows from the Karoubi density theorem, not from anything fancy. No Oka is involved in this particular discussion. So curly C of G is something which started out life in algebra. We started out life as a modification of curly A. It started out life, by the way, living just on the minimal principal series, but now this curly C algebra is mapped to the reduced C star algebra, and it sees all of the discrete series, for example, which don't live in the unitary principal series. They live elsewhere. It sees everything in that the reduced C star algebra of G sees. At least at the level of K-theory, as I've indicated here. So we have a new perspective on the C star algebra of G, namely as a quotient, or essentially as a quotient of some large Frachet algebra by some kernel, some interesting ideal. And that's not literally true at the level of the algebra, but at the level of the K-theory, it is true. And back in the day, people wanted to know, Alain and Gennady wanted to know, what is the K-theory of the reduced C star algebra of G? And they had a conjecture, which we'll get to in due course, but let's call the Kasparov problem, the problem of calculating the K-theory of the reduced C star algebra of G. And obviously it comes down to two things from the perspective of this talk, namely, what's the K-theory of this mysterious ideal, the kernel of alpha, and what's the K-theory of this maybe less mysterious, I don't know, of this algebra curly C of G of S. If you know the answers to these two questions, then thanks to the K-theory six-term exact sequence, then in theory, in principle, you know what the answer to the question, what is the K-theory of the quotient algebra, and therefore, because the quotient algebra identifies with a reduced C-star algebra at the level of K-theory. And therefore, you understand the answer to the Kohn-Kasparov problem in an interesting and roundabout way. And what I want to do is to explain to you that the first problem is a Langlands type problem. It's related to the Langlands classification. And the second problem is an Oka type problem, and it's related to the Oka principle, or if you like, Novodvorski's theorem, as we were discussing it at the beginning of this talk. How am I doing? I guess I'm doing okay. You said you want me to talk for like an hour and a half or something, right?
Yeah. So you are still good to go for 35 minutes.
Yeah. It may not be another 35 minutes, but on the other hand, it will certainly be more than 5 minutes, so somewhere in between. Okay, just to summarize, people want to know, or did want to know back in the day, what is the K-theory of the reduced C-star algebra of G? In many ways, this is still a pertinent question. You can, just because you know the answer to what is the K-theory from a certain perspective, it doesn't mean it's not interesting to answer the same question again in a different way, and that's what we're talking about here. And if you do want to know the answer to that question, from the perspective of what I've been telling you, it breaks up into two sub-questions, and let's try and understand the nature of these two questions one at a time. Here's the first one. When you look at all of the minimal principal series representations, you remember that I made a little bit of a to-do to say that I didn't want to assume that mu had this dominance condition which appears in the Langlands classification. It was convenient not to put that in because that specified an open subset of our base space rather than the closed subset, and I'd have to take the closure anyway. And so I decided not to mention dominance when I constructed the algebra A of G of S and then constructed the algebra C of G of S. But on the other hand, if I restrict to the dominant points, the points where real part of mu is dominant, then I capture the full essence of this algebra because there are intertwining relations among the representations where mu is dominant and the representations where mu is not dominant. There's some Weil group acting. And so if you restricted to the dominant chamber, this map, the restriction map, it would be 1-to-1. It's a little more convenient to restrict to the closure of the dominant chamber, because then, as I say, that's a closed subset. And think of C of GS as an algebra of continuous functions on some closed chamber. For instance, in the case of SL2, there's an algebra of continuous functions on half spaces, not whole spaces, including the vertical boundary line. That's one thing I want to mention on this slide. The other thing I want to mention on this slide is that we're dealing with Frechet algebras, and it's important to pay attention to how those Frechet algebras are defined. We don't worry about this sort of thing when we're doing K-theory of C-star algebras, but here in Frechet algebras, it's kind of important to understand exactly what the support conditions are for K-theory. I said that on each tube, if I bound the real part of mu, on each tube, I should have rapid decay in the imaginary direction. If I restrict to such a tube, then the restrictions on the tube give me another Frechet algebra. So this is the algebra of continuous functions just defined on the tube, which rapidly decay in the imaginary direction. And the original Frechet algebra is just the inverse limit of these tube Frechet algebras, let's call them that. And there's one for each number n. And when you take the K-theory of a Frechet algebra, which is an inverse limit, then roughly speaking, the K-theory of the inverse limit is the inverse limit of the K-theory. There's a lim1 sequence, but that's basically what's true here. So the relevant topology, if you're thinking topological K-theory, the relevant topology here is the topology of strips, so the topology of tubes, rather than the topology of entire half spaces, like in the pictures that I was drawing for you. So what I'm going to do is I'm going to focus, because of this lim1 sequence, because of the fact that C is an inverse limit, and because K-theory more or less commutes with inverse limits, I'm going to focus on one of these algebra of functions just defined on a tube like this, because that's a more accurate rendition of what this algebra is all about, rather than considering functions defined on all of our chamber. Let's take a look at I have some exercises for you. There are 3 homework exercises. Let's take a look at SL2 again. Now, what I'm interested in is the ideal. I'm interested in trying to show you that the ideal, which was the kernel of this canonical homomorphism to the C-star algebra, I'm interested in trying to understand that this ideal has manageable K-theory. And so I'm going to do a little calculation, or actually I'm not going to do a calculation, you're going to do the calculation. And the calculation involves, well, first of all, the bit I'll do is I'll tell you what this kernel looks like. As I say, we're just looking at functions on a strip, a tube in 1 dimension, if you like. And we're just looking at the dominant part of the vector space. So we're looking at functions defined on a strip which is bordered by n on one side and 0 on the other side. That's the dominance condition. So the real part of z should be, well, dominant means strictly bigger than 0. And if you close that up, bigger than or equal to 0. And what about the kernel? Well, here's what the kernel looks like. Before I wrote down an algebra for SL2, which was a direct sum of a 2x2 algebra and a 3x3 algebra. Here, just to make my life and your life simple, because you have to do the homework, I'm just studying the 3x3 part. Actually, the 2x2 part's a doddle. It's much easier. Here's what the ideal looks like. It's just functions defined on a strip. And there are 2 constraints on the function. One is that the restriction to the imaginary axis should be 0. And the other is that when you evaluate at 1, this is one of the points where something interesting happened previously. When you evaluate at the point 1, you should get an element which has this form here. I believe there may be a typo here, and instead of writing a column of, no, I guess it's okay. I take it back. You get this picture here. Previously, when I showed you what the algebra curly C looks like, I said that something special happens at f of 1. And previously, what I insisted is that we study only functions which are 0 in the 4 places indicated by white zeros. But now, because we're in the kernel of this evaluation ideal to the reduced C-star algebra, I pick up 2 more zeros. That's because the orange zeros correspond to discrete series representations, which are in the tempered dual. So if when I restrict to the reduced C-star algebra, if when I restrict to the tempered dual, I get 0, then the matrix value of f at the number z equals 1 has to be 0 in the 2 orange places. The white orange places you get for free, they're 0 anyway. That comes from the definition of the algebra, but the orange comes from membership in the ideal. And that's what's happening along the imaginary axis as well. When you restrict to the imaginary axis, every representation that you see there is each of these irreducible principal series representations is already a tempered unitary representation. These are the unitary spherical principal series. So when you restrict to them, you have to be 0 if you're in the kernel of the homomorphism, which is restriction to the tempered dual. So we have these supplementary conditions on functions. They're continuous functions on this closed strip. They should vanish at infinity, well, rapidly, as the imaginary part of z goes to infinity. And moreover, on one edge of the strip, the function should be identically 0. And there's only one other thing to say, which is that at the special value 1, the matrices should assume this particular form. I'm going to assume that n is bigger than 1. Otherwise, let me do, as you see in green, the kernel of alpha is not actually well defined until n is bigger than 1. And now it's a certain Fréchet algebra. And so you can ask what is the, I mean, it's an easy Fréchet algebra of continuous functions. You can ask what is the K-theory, and the answer is it's 0. That's the little exercise. More or less, it's Morita equivalent to just continuous functions on the strip, vanishing at infinity, which are 0 on the left-hand side. And that's now a contractible space in the sense of locally compact spaces. And so you're done.
And I just heard when you say that this holds for all examples, you mean for all these capital N's, right?
For all capital N's, also for all capital S's. If you change this finite set of isotypes and you make it bigger, you'll get more complicated algebras with more special constraints at more points. And so you have to study all of those, but they all work out the same way. Because you're throwing away the tempered representations, these algebras have satisfy constraints at f of 1 and f of 3 and f of 5, for example, if S is a set of even numbers, constraints which are simplified. There are more zeros, and that's enough to make the K-theory zero. I'll show you a couple of other examples in a moment.
Thanks.
That's encouraging. You have to be a little bit careful because we're only dealing with SL2 here, and it's kind of special. I mean, the advantage is you can actually see what's going on, but it's a little bit special. Here's a first sense in which it's kind of special. I said when I was discussing the Langlands classification, and I indicated again on the last slide, that when you study representations which appear in the Langlands classification, these induced representations with their irreducible Langlands quotients, I said that for SL2, the kernel of the map from the induced representation to the Langlands quotient is always a tempered representation. So that's, well, that's true for SL2. It's also true for SL2C. But I asked Birgit Svea about this. I presented her with a stupid conjecture, and she pointed out to me that it's only true for SL2R and SL2C. So it's much more complicated what happens in general. If you look at one of these, here, let me use my little pointer, one of these parabolically induced representations, which maps down to a Langlands quotient, the kernel of that quotient map is rarely a tempered representation. Generically, it's not a tempered representation. Incidentally, it's generically far from being irreducible. There's usually an incredibly complicated composition series which describes the decomposition of each of these induced representations into irreducible. People don't know what the composition, they know what the composition factors are, that comes from the Kashtan-Lustig conjecture, but they don't know the exact structure of the lattice of subrepresentations. So it's very complicated what happens, whereas for SL2R it's extremely easy. Okay, and so here's an example to kind of illustrate this. Here's a plausible result of a calculation. This is the sort of result that you might get if you were dealing with a slightly more complicated group, a real rank 1 groups, because there's just one complex variable here. For example, SU21, this sort of thing could, in theory, until you think about it, occur for SU21. There may be 2 special points instead of 1. That's very commonly the case. So here we have a condition at f of 1 and a condition at f of 2. In this real rank 1 situation, it's true that the condition at real z equals 0 is the same as it was before. But maybe what happens at f of 1 and f of 2, as I've written it here and here, maybe we see our Langlands quotients, A and B at 1 and 2 respectively, but maybe the Langlands quotient at 2 appears as a subrepresentation at 1, and maybe the Langlands quotient at 1 appears as a subrepresentation at 2. I mean, why not? Why you know, this, until you think about it, that could easily happen. This is I've described an algebra here which is plausibly like an algebra which could occur as one of these kernels. There's a unique irreducible quotient at every point, just like Langlands tells us. It's generically irreducible, just like we know. Along real part of z equals 0, it's 0 just by virtue of tempered representations. It's plausible that this is exactly what happens, but now you calculate the K-theory of this thing, and it's kind of a shame. You don't get 0. I mean, you just get what you get, but you don't get 0. So it means you have to be careful. And the good news is that this sort of thing cannot occur. There's a sort of hierarchy to the Langlands classification. I didn't explain anything about how you prove the Langlands classification, but it's done by attaching to each irreducible representation a set of what are called exponents. Those are mu's. You attach a set of mu's to each irreducible representation, and then you match the mu's to realize a representation as a Langlands quotient. And there's something hierarchical about this in the sense that the mu that appears in the Langlands quotient is always bigger than the mu's which appear in the Langlands, so to speak, the Langlands kernel, the kernel of the map to the quotients. So it's impossible to have, as I showed you on the previous slide, B is a subrepresentation of the representation whose Langlands quotient is A, and A is a subrepresentation of the representation whose Langlands quotient is B. That violates the hierarchy of exponents. What is possible and what does happen for SU21 is a picture like this. Oopsie. Like this. So now what this is showing you is that when you evaluated f is equal to 1, the kernel of the map to the Langlands quotient is tempered. And so in this kernel ideal, it's just 0. That's where this 0 comes from. Okay. On the other hand, the kernel of the map to the Langlands quotient at 2 is not tempered, but it's the representation which appears as the Langlands quotient at 1. This sort of thing does happen. And so you have to worry about this, but now you can calculate the K-theory of this and you get 0. So that's nice. In fact, we did this for all rank 1 groups, and that's about where we are now. I think I maybe said that's on the next slide. Yeah, this, almost. So that's one issue explored a little bit about understanding the K-theory of these algebras. The algebras are all very elementary. They're just algebras of matrix-valued functions. I mean, how hard can it be to understand the K-theory? You can calculate anything given enough time. But there are an infinite number of examples, so you need to be systematic somehow. And the point is that the Langlands classification gives you some systematic tools to do these calculations. Anyway, there's a second issue, which is that when you study higher rank groups, higher real rank groups than SL2, for example, I'm drawing a picture here for SL3, instead of studying half planes whose real parts are half lines, the role of the half line gets replaced by a closed chamber like the one you see in green in this picture. And now the boundary of this chamber doesn't just consist of the place where the real part of mu is 0, it consists of two hyperplanes where the real part of mu is more or less 0, 0 in one direction, so to speak, and then one joining point where the real part of mu really is 0. So it's more complicated than what I was discussing before. And you have to worry about what the functions in our algebra C of G look like when you restrict them to these root hyperplanes. And the good news is that Langlands also tells us about that, because that's the rest of the Langlands classification. The other hierarchical part of the Langlands classification is that there's a hierarchy of standard parabolic subgroups, and that plays a role in making sense of the structure of the algebra C of GS in this case, and more importantly of the kernel of alpha. And so it's, let me put it this way, plausible to say that in general, the K-theory of the kernel of this ideal is 0. I certainly wouldn't say that we've proved this, but I would say that we've proved this to within a single set of quotation marks in rank 1, real rank 1. And in general, we're still working on it. Okay. I said that to understand the K-theory of the reduced C-star algebra, you could break that problem into 2 bits, and one bit had to do with calculating the K-theory of some ideal. And the bottom line is that the K-theory of this ideal is 0. That's where we are now. So that's an understandable answer. You can't argue with the K-theory as 0. Nothing is simpler than that. What about the other thing? The other problem was to understand the K-theory of the algebra C of G of continuous matrix-valued functions on these tubes, which satisfy some Lie algebra conditions everywhere and also some rapid decay conditions. That's what we were talking about. What is the K-theory of this thing? This is a strange algebra not studied in representation theory as such, because it's not a convolution algebra of functions on the group. It's just what it is. You know, it's not although it restricts and gives a map to the C-star algebra of G, it's not by itself the convolution algebra of any sort. It's not like the max C-star algebra or the max Banach algebra or anything like that. It's just nothing. On the other hand, you can make a minor modification to the definition, and then we get into much more familiar territory. So let me write down, I call this a newish Frechet algebra. It's only new-ish because all I did was I copied the previous definition exactly. And the only change I made was I replaced continuous by holomorphic. That's the only change. Oh, and I called the algebra H for holomorphic instead of C for continuous. Otherwise, this algebra is exactly what I said before. So it's holomorphic matrix-valued functions, which obey Lie algebra conditions at any finite set of points and which converge rapidly to 0 in the imaginary direction. Some other Frechet algebra. If you have holomorphic functions, you can see that things are going to be quite different from what they were before. If you have a holomorphic function on, this space that we were describing, and you restrict it, as we were doing with the homomorphism alpha, if you restrict it to the tempered dual, actually that restriction map is going to be one-to-one, because roughly speaking, the Langlands tells us that the tempered dual is like a totally real submanifold of the admissible dual. The admissible dual is a complexification of the tempered dual. So if a function, holomorphic function, vanishes on the tempered dual, it's going to vanish identically. There's no point in studying a kernel alpha like we did before. So we have to do something else with this new algebra. Here's something you can do. I don't think this will be a surprise to anyone, since it's obviously what's coming up. You can guess that there's an Oka principle in this case, and that by replacing continuous functions by holomorphic functions, or maybe holomorphic functions by continuous functions, you don't affect the K-theory. So the holomorphic algebra obviously is a subalgebra, in fact, a closed subalgebra of the continuous algebra. And you can conjecture that the inclusion induces an isomorphism in K-theory. This is, of all of the various theorems and quasi-theorems, theorems in one quotation marks, two sets of quotation marks that I've mentioned, this is the most tenuous, and so I didn't even call it a theorem at all. I just called it a principle. However, Jacob Brad, my collaborator, did check this for SL2R, and it's okay for SL2R. We have reason to believe that it ought to work in general. I mentioned the name of Bernstein and a couple of his former students there, Braverman and Gates-Gorey, who studied the structure of A of GS and have proved theorems about A of GS, which I think are very, very relevant to this problem. Maybe I'll mention that in a moment. So it's a conjecture, if you like, that I've written here, but it's not a totally uninformed conjecture based only on optimism. We have some reason for making this. And at least for SL2R, maybe by now SL2C, I haven't talked to Jacob in a couple of weeks, this thing is definitely true.
Sorry, Nigel, and what did you mean by this new approach to Novodvorsky theorem?
Yeah, that's what I'm going to describe on the next slide. Yeah. So as I mentioned at the beginning, when we got serious about this, we decided, well, let's start by understanding Novodvorsky's theorem a little bit better. Not just by boiling it down to Grout's theorem, but just by proving it from first principles. And so let me just have just a couple of slides explaining what's going on there. So back to the world of Novodvorsky, remember we had certain Banach algebras, B of K. Each time K was a reasonable compact subset of Cn, a so-called polynomially compact subset of Cn, you could build an interesting Banach algebra, B of K, whose Gelfand spectrum is K, and whose Gelfand transform is the inclusion of B of K into C of K. And now you want to prove that the K-theory of B of K is the same thing as the K-theory of C of K. Well, if that's true, then, and you can replace the B's by the C's everywhere, then certainly we know that if you break K into two bits, K prime and K double prime, like I've shown you in the picture, there's a Meyer-Vietoris sequence. I mean, that's true for topological K-theory, so it needs to be true for these B algebras as well, if Novodvorsky's theorem is to be true. And so you might spend some time thinking about this Meyer-Vietoris principle. And this turns out to be the main step. This is what the people who study the Oka principle understand very well, what we just translate into K-theory here. And in fact, this is the main step in the argument, and let me try and explain why in terms of just a cartoon here. First of all, there's a wonderful theorem of Jean-Benoît Bost about when you have Meyer-Vietoris, and it's a beautiful theorem. It's not known that much because we study K-theory of C-star algebras, and this theorem has no content whatsoever for C-star algebras. But in Banach algebras, it's extremely interesting. Suppose you have a pullback square, like I've shown you there, and suppose the following conditions are satisfied. First of all, the range of one of the maps into the right-hand corner has to be dense. That's a minor thing. The main condition is that the range of the two maps into the corner add up algebraically to the corner. So the range of phi prime plus the range of phi double prime is, the algebraic sum is in this case, a triple prime. That's an algebraic condition. I'm not saying the closure is that, I'm saying it is that, okay? In that case, there's a Meyer-Vietoris sequence. If you have this type of pullback square, then there is a Meyer-Vietoris sequence. That's a beautiful result of Jean-Benoit. I want to explain how it's true, why it's true. But it applies beautifully here because this range plus range condition is exactly the sort of thing you see in holomorphic functions. It's like the theorem B of Cartan. If you have a holomorphic function on an intersection of two open sets, as long as the union of those two open sets is reasonable, as Stein is polynomially convex, then any holomorphic function on the intersection can be written as a sum of holomorphic functions, one on one of the bigger sets and the other on the other bigger sets. That's Cartan's theorem B. And so the theorem of Bost is designed, I mean, was explicitly by Bost designed to apply to situations in which complex variables enter into the picture. And so it's not a surprise that it should be useful here. Here's how you can actually use it to understand the Novodvorský theorem. You take a polynomially convex set in green, like you see up here, and you want to understand what is the K-theory of this algebra. In fact, explicitly, you want to understand the Gelfand transform, the fact that the Gelfand transform is an isomorphism for this open set, excuse me, not open set, closed polynomially convex set. Well, that's just with a sharp knife, like a samurai sword, you slice it into two pieces like this, whose intersection is this bar here. And you argue that it's like a 2 out of 3 principle. If the Meyer-Vietoris sequence, if the Novodvorský theorem is true for K prime and for K double prime, it has to be true for K itself. Actually, it's more convenient to say that if Novodvorský failed for K, it would have to fail for one of K prime or K double prime. I guess I should use X's. If it failed for X, then it would have to fail for one of K prime or K double prime, maybe this one here. Okay, well, then you take that polynomially convex set and you slice it into two. And if the theorem failed for the set with the ugly X in it, it would have to fail for one of these two fellows as well. Maybe it's this one. And if there was a failure here, there'd have to be a failure after one more slicing down here. Maybe it's this one here. And you just keep going. And if you keep slicing again and again and again with a sharp enough knife, in the end, what you will see in the limit is a polynomially convex set, but it'll have one lower dimension because it'll live in a hyperplane. And so if there's a counterexample to Novodvorský in dimension K, there's a counterexample, I should say N, real dimension N. There's a counterexample to Novodvorský in real dimension N-1. But of course, in dimension 0, Novodvorský is definitely true. There's no doubt about that. In dimension 0, there's no difference between holomorphic and continuous. So that's how you prove Novodvorský's theorem. And it's critical in all of this that there's some version of theorem B so that Bost's theorem applies. And going back to the algebras, let me just go back a couple of slides that we were discussing here. What Jacob was able to take advantage of for SL2R is the fact that the algebra H of G of S for SL2R is actually a free module over its commutative counterpart, which is just the even holomorphic functions on a strip. It's a free module. And to check Bost's condition for an algebra, which is a free module over some commutative algebra, it just means you have to check Bost's condition for the commutative algebra.
Sorry, Nigel, and what's the rank of this module?
The rank of H of GS, I mean, it depends on what S is. If you look at that 3x3 example that I was showing you, then the rank is 9. It's just there's one rank, so to speak, for each matrix entry.
Mm-hmm. Yeah.
And so we're able to apply Bost's theorem to get a Meyer-Vietoris because we can reduce from a non-commutative algebra like H of GS to a commutative algebra when it comes to checking the hypothesis of Jean-Benoit's theorem. And so we're done. Now, what Bernstein and Braverman and Gates-Gorey did is they showed that although these algebras are not known one way or the other to be free in general, they satisfy a certain local freeness condition, and it's plausible to believe that that local freeness condition is enough to make the argument work rather than a sort of global freeness by another Meyer-Vietoris sequence argument. Okay.
And I'm sorry, Nigel, it might be a stupid question, but why did you say that this Bost theorem is vacuous for sister algebras?
Oh, because here we go. The range of any C-star algebra homomorphism is closed.
Yes.
So I didn't really make a big fuss out of this, but a necessary hypothesis is that at least one of the maps should have dense range. So at least one of these maps should be surjective.
Yes.
In the C-star algebra context.
Exactly.
And so it's not exactly vacuous, but it's now the usual May-Vietoris sequence in C-star algebra K-theory.
Okay.
Yeah, vacuous is probably putting it a bit strong. There's no interesting case in C-star algebras where this range plus range condition applies. If this applies, it's together with this fellow, it's because one of the ranges itself is all of A triple prime.
Yeah, I missed this part with the density, yes.
Yeah, sorry. It was there. I put it there for the lawyers, but I didn't make a big deal of it.
And it came useful.
Oh. And it came in. All right. There's one more thing to add to all of this, excuse me, which is a final discussion of the algebra curly H. And now I'm going to introduce yet another algebra, another fresh algebra, but this one is well known in representation theory. It's called curly S of G. It's often called Castleman's algebra, after Bill Castleman. This group is a manifold, of course, but it's not just any manifold. All reductive groups are defined by algebraic equations, and that makes the reductive group into what's called a Nash manifold. It's just a manifold defined by algebraic equations, basically, real manifold. And each time you have a Nash manifold, it comes just by birth with a natural Schwartz space, S of G, curly S of G. And in the case of a group, this natural Schwartz space is a convolution algebra. So the geometry of G itself gives rise to G, the manifold G, not the group G, the manifold G gives rise to a convolution algebra, Castleman's convolution algebra. It's not Harish-Chandra's algebra, which is an altogether more mysterious thing, which is defined using the geometry not of the group, but of the tempered dual of the group. It's a little strange. It's defined in a completely different way. But the Schwartz algebra of Castleman is a natural convolution algebra, not Harish-Chandra's algebra, and nor is it holomorphically closed in C star reduced to G. It is dense, but it's not holomorphically closed, not by a long shot.
Sorry,
on the other hand, it's...
May I ask? So this holomorphically closed mean closed under holomorphic calculus, yes?
Yes,
Okay,
exactly.
it's not true for this algebra.
It's definitely not true for this algebra. This is, it goes, well, I don't know. It's not true. I was going to say it's definitely catastrophically false for this algebra, but maybe once it's false, it's just false. I don't know. Just, I wanted to make a big deal of it, as you saw that I did. Anyway, it's a convolution algebra now. It's a real honest-to-goodness convolution algebra of functions on G. So it's represented as operators on any space on which G acts, and in particular on each of the fibers of our big vector bundle that we introduced, which carries an action of G. Previously, we used the Lie algebra action of G, but now we can use the group action of G to build a representation of this convolution algebra. Again, I've done some compression by a finite set of K-types to build a representation of this convolution algebra in each fiber of our bundle. And overall, as you vary from fiber to fiber, what you can easily check is that the convolution algebra acts through operators or elements of H of GS. So as you vary from fiber to fiber, the action of an element in the Castleman algebra, what you find is that the actions depend holomorphically on whichever base point you're dealing with. And so you get a holomorphic function out of the action of Castleman's algebra, not a continuous function. Not only that, but this map is basically an isomorphism. For SL2, once again, we proved on the nose that this is an isomorphism. It's always one-to-one, and for easy reasons, but it's actually an isomorphism for SL2, and probably it's an isomorphism in general. The way I've phrased all of these algebras in today's talk, I stole I don't know, the perspective on these algebras from Eric van den Baan and his collaborator Soifi, whom I don't know. And my strategy as regards this isomorphism or potential isomorphism is just to trick Eric into proving it for me. So I don't think this is going to be a big deal for people well versed in Paley-Wiener type theorems, which is all about computing the ranges of Fourier transforms. And in an emergency, if it's not true, it should still be true at the level of K-theory. Yeah, you have a question, Adam.
May I ask again? So you mean that this map induces isomorphism in K-theory, or is it plainly isomorphism?
It's definitely an isomorphism on the nose in the case of SL2, and I'm suggesting that it's going to be an isomorphism on the nose at the level of algebras, at the level of Fauché algebras always.
Ah, okay. Okay. Thank you.
There are many Paley-Wiener theorems already proved for this or that convolution algebra of functions on G. It just so happens that this particular convolution algebra of functions, the Schwartz algebra, is not being considered. So that's a little unfortunate for us. But we hope, as I say, we hope to trick the harmonic analysts into proving this for us. And maybe one final part of the puzzle. Here's our old friend, the Kohn-Kasparov conjecture, or the Kohn-Kasparov isomorphism. One of the ways of formulating this, which was was integral to the way that Laforgue approached the Kohn-Kasparov conjecture, is to say that the Kohn-Kasparov homomorphism, the map which Kohn and Kasparov conjectured to be an isomorphism, is the map in K-theory induced from the inclusion of this Bill-Castleman algebra into the K-theory of C star of G. What's going on here is that the left-hand side, the K-theory of curly LS of G, it's relatively easy to calculate that using the dual Dirac method. There is no gamma element obstruction when you're dealing with curly S of G. The gamma element obstruction has to do with our obligation as C star algebraists to deal with unitary representations. But if you work with the Castleman algebra, you don't have to deal with unitary representations at all. I mean, you don't have to constrain yourself to dealing with unitary representations at all. So this fundamental dream in KK theory that gammas should always be one, I'm talking about Kasparov's famous gamma element, this dream is actually the reality if you deal with the Castleman algebra, not the reduced C star algebra. So the left-hand side is really, really easy to understand, relatively really, really easy to understand in K-theory. The technology of the 1980s is entirely adequate to understand it. And then you check the diagrams and you see that the inclusion map corresponds to the Baum-Kahn assembly map, if you like. It corresponds to the assertion that the inclusion map is an isomorphism in K-theory corresponds to the assertion that the Kohn-Kasparov map is an isomorphism, or if you like, the Baum-Kahn assembly map is an isomorphism for the group G. Back to the picture at the beginning of the lecture. Here are the various bits and bobs that were there. Now I can fill in what the K-theory groups are. We had our algebra curly C, which mapped to the reduced C star algebra. And thanks to the Langlands classification, we have, with a high degree of certainty, the assertion that that map is an isomorphism in K-theory. With a lesser degree of certainty so far, we have the isomorphism, the Orca principle, which says that the algebra of continuous functions that I defined has the same K-theory as the algebra of holomorphic functions. Then with very high degrees of certainties, we have some Paley-Wiener isomorphism at the level of algebras over the top. I wrote a little question mark next to the Kohn-Kasparov isomorphism going vertically down, because strictly speaking, we're looking at something slightly narrower than the Kohn-Kasparov isomorphism, in which I'm dealing with these relativized or compressed algebras, compressed to S. What we're really interested in is forming one of these diagrams for each finite set S, and then taking the direct limit of the diagrams as S goes to infinity. In which case, what you'll get on the left-hand side is the Kohn-Kasparov isomorphism, known to be an isomorphism. And so there's an interesting story which blends together a number of different places, some Fourier theories, some complex geometry, and this remarkable theorem of Langlands that I mentioned before. I just have one more slide. I'm just going to show it very quickly to explain what's going on here. I didn't have time to explain why Langlands' theorem is the way it is. But the fact of the matter is that the proof is very concrete, and it involves definite objects and definite formulas. It involves ideas about parabolic subgroups, which I didn't emphasize at all. The fact that the parabolic subgroups are actually defined dynamically, not as upper triangular matrices. That's just what they happen to turn up looking like. The actual definition of a parabolic subgroup is something very dynamic. It has to do with the action. I've drawn a picture here. This is supposed to be the action of G mod P. Some flag variety for SL2, it's just the projective line. This is the action of the diagonal A subgroup on RP1. And what you see is that it moves, it flows from the South Pole to the North Pole in a very interesting way. That the dynamics of that action correspond to Langlands' famous limit formula, which I won't try to parse for you now. And the limit formula is really all you need to prove the Langlands classification. So there's a lot of if you're an optimistic person, there's a lot to steal from here. And if you're an optimistic person, you might find in all of this, in the internal workings of the Langlands classification, something of greater significance back in the world of Baum-Cohen and discrete subgroups. However, I'm just saying you might. It's just a very interesting speculation. All right, thank you very much.
Thank you so much, Nigel. Let's find the icon for clapping hands.
Thank you.
Yep, great. And now we can start with our questions. So please fire at will. Go ahead, Alan. Oh, Alan, cannot hear you.
Yes. Oh, well, okay. I mean,
Right.
is there a place for the Langlands dual?
Good question. You mean in non-commutative geometry, or do you mean in this argument?
No, I mean in this framework. Yes, yeah.
I would. I mean, what the Langlands classification tells you is that for a single real reductive group, the representations of G are classified by homomorphisms into the Langlands dual. You can read that off the set
Exactly,
of Langlands
yes.
data.
Right.
I don't know how to, that's just checking parameters, if you like.
Yeah, it is a
I don't
checking
know
of
how to-
parameters. Yes, yeah.
Yeah, I don't know how to put it in an integral way.
Well, what I had in mind was perhaps from this example, one could try to infer some more general type of duality in general, not only in that framework. That was the meaning of my question.
Yeah. My feeling about this, as regards my own thinking, is more or less the same as that I tell Jacob, which is that you got to keep your feet anchored on the ground, do SL2 first, and nail down every last
sure.
part of the argument and so on.
Sure.
I spent. I've done it 3 times now. I taught the Langlands classification 3 times, and I'm supposed to teach it again next year. And I think I'll finally understand it after I've taught it 4 times. And so I've made a serious commitment to, if you like, prepare to answer your question.
Okay,
but I did not yet. I did not yet advance to having any suggestion about how I might do what you say, use the Langlands dual group in a serious way.
Okay, any further questions, please?
I have a question.
Go ahead, Tom.
Is there a kind of polynomial convexity condition of sets of complex parameters of Langlands, but phrased in terms of representation theory?
So let me see. So we know that the overall parameter spaces, as I showed you, they're basically complex vector spaces. I guess you'd like to say that if you take a collection of admissible irreducible representations, which constitutes a polynomially convex set, there should be some statement about that just in the language of representation theory. Mm-hmm. They should have collectively some property, presumably some convexity property. I don't know. could imagine quite easily producing something, facile. So I think I could produce some kind of answer to your question, but I don't know if I could produce a meaningful answer. Certainly, I don't know one right now. But yeah, interesting question. Well, one thing to keep in mind, well, maybe that doesn't apply here. I mean, there are some particular examples of polynomially convex sets to which you could study as test cases. So, for example, if you take a complex vector space Cn and you multiply and you embed any x into Cn, and then you embed x diagonally into Cn times the complex conjugate of Cn. So if you put x diagonally into Cn times Cn bar, then that's always polynomially convex. And I guess you could try and interpret what such an embedding would be in representation theoretically. Maybe it would give you a chance to formulate a conjecture. That's the best I can do.
Okay, thank you for this answer. I would like to ask a question which is gone about this Langlands dual, but is there a relation between these algebras, Castleman algebra, HGC of G of S, CGS, with the Langlands dual?
I don't see.
Besides Oka principle and all this stuff.
Yeah. I don't think it's likely that to be so, just because of the strange way in which this duality works. Representations on the one hand are basically corresponded to conjugacy classes on the other. I think it would be hard to, if you're studying the two groups by studying both of them, they're convolution algebras. That doesn't sound quite right. That sounds like the wrong thing. You should do two dual things to these two dual groups to get two things which are then comparable directly.
Okay, thank you.
All right, anybody else? Richard? Nope.
Maybe just one more.
Go ahead.
Question. Since I don't know, I probably miss it. Could you please remind me what does it mean for this admissible representation to be infinitesimally equivalent? It was at the beginning.
Yeah, it means, it means one of two equivalent things, one of which is purely algebraic and the other is more Banach space theoretic. Let me give you the Banach space theoretic one, since it's more that kind of seminar. Suppose you have two representations, two Banach space representations of the same group. You could imagine building an intertwining operator from one of them to the other, which is one-to-one and has dense range. Okay, and you could say that the two operators are then, I don't know, infinitesimally related if there's an intertwiner which is injective and has dense range, like that. So that
so almost
morphisms in Banach spaces which are injective and have dense range, those are both mono and epi morphisms, but they're not necessarily isomorphisms. So if you take that relation and you make it into an equivalence relation by studying chains of arrows going backwards and forwards, that's infinitesimal equivalence.
Okay, so we drop the condition of being surjective, but
yes, exactly.
Try something like isomorphism, but
yeah, exactly. Change isomorphism to mono plus epi.
Okay. Thank you.
Any further? Yeah. Any further questions? I don't see any raised hands. Alain, would you still like to ask some question?
Oh no! I see. I appreciated a lot of the talk.
You carry a heavy burden, Alain, more than the speaker. I think you have to be ready to comment wisely on every talk, no matter what it's about.
I find it quite fascinating.
Well, I'm very glad to have you here.
Yeah, this is wonderful. So to the final question, let me ask you, Nigel. It's very, of course, simple, but is when you look at your map alpha, which was an important player in your talk, do I understand it correctly that its image is dense?
Yeah.
Okay, just to make sure I want it. Okay, so in this case, let us thank Nigel again. So we have an icon of clapping hands. And I pronounce the end of the academic year, 2020-2021. This was a crazy year, fully on Zoom, Zoom teaching, Zoom seminar. But I think it was still quite exciting mathematically. And I hope to meet you again in October 2021. Even if we are allowed to go to the classroom, we will not relinquish Zoom. Definitely the Zoom aspect will prevail. And we also keep the hour to have our American friends on board together with us here in Europe and some parts of Asia who can turn in despite the time difference. I think we went as far as India. During Alan's talk, there was one guy from India. So for them, it was like 10 p.m., but they still can manage it. So we had from California, 8 a.m. to India, 10 p.m. This was the spectrum at Alan's talk, for instance. So I think this is precious, and I want to keep it this way. For the time being, thank you very much. Let me just announce that Masoud Kalkali is already signed up as a speaker for the next semester, and we are working on the rest. Okay, so thank you guys, and I hope to see you in the next academic year. Thanks. Bye bye. I stop recording.
Bye bye.
Thanks everyone.
Thank you,
Bye-bye.
See you in October.
Thank you, everybody.
Thank you.
Bye bye.